Ladies and gentlemen, in this session we will explore NWC's next-generation structural health monitoring technology, BOTDA. This system uses optical fiber to continuously monitor the condition of infrastructure in real time, enabling seamless measurement without blind spots. Traditional point-based sensors often suffer from data gaps between measurement locations. However, with advanced technology, a standard optical fiber can now be transformed into a massive continuous sensor spanning up to 120 kilometers. This system completely eliminates measurement blind spots and enables real-time collection of structural health data across large areas, significantly improving monitoring efficiency. It represents an innovative engineering solution that dramatically enhances the precision and reliability of large-scale infrastructure management. When laser light traveling through an optical fiber interacts with acoustic phonons, it produces a phenomenon known as the Brillouin frequency shift. This shift changes linearly with variations in temperature and mechanical strain. As shown in the graph, by precisely measuring this frequency shift, we can analyze changes in the physical condition of the fiber in real time. When combined with OTDR time-domain technology, the system can also determine the exact location where an external stimulus occurs, making it a key technology for structural monitoring and many other engineering applications. The key principle behind BOTDA technology is that the Brillouin frequency shift reflects the combined effect of temperature and mechanical strain. However, there is an important engineering limitation. When a change of about 10 MHz is detected, the system itself cannot directly determine whether the shift was caused by temperature variation or tensile strain. Therefore, achieving precise interpretation requires more than measurement alone. Contextual analysis through software and advanced algorithms plays a crucial role in accurately distinguishing and interpreting these changes. To overcome CPU bottlenecks caused by the massive data load of high-precision sensing, we introduced an SVR acceleration solution based on FPGA parallel matrix computation. This approach increases processing speed by 42 times compared to a conventional Intel i7 CPU, enabling true real-time dynamic monitoring. At the same time, power consumption is dramatically reduced, achieving over 226 times greater energy efficiency. As a result, this architecture provides an optimized hardware acceleration environment that simultaneously delivers high-performance computation and ultra-efficient power design. Let's examine the practical meaning of 120 kilometers in BOTDA-based fiber sensing by comparing two different system architectures. In a standard loop configuration, a 120-kilometer optical fiber measures an effective sensing range of about 60 kilometers. In contrast, our patented bidirectional architecture combines a main unit with a remote unit, enabling full coverage of the entire 120-kilometer span. Depending on the power conditions at the site and the required monitoring distance, users can choose the most suitable solution, either a single-ended configuration or a high-performance bidirectional architecture. This system delivers industry-leading performance with both standard and specialty optical fibers, and in a dual-ended configuration, it enables precise measurements over distances of up to 120 kilometers. With a plus or minus 2 GHz scanning range and ultra-high strain measurement accuracy, the system can support extreme conditions, from minus 270 degrees Celsius to plus 700 degrees Celsius when using specialty fibers, and strain levels of up to plus or minus 3%. These extreme performance limits are determined not by the analyzer itself, but by the intrinsic physical properties of the optical fiber, clearly demonstrating the exceptional hardware capability of the system. This solution dramatically improves monitoring precision in industrial environments by combining distributed sensing technology with zero dead zones and advanced algorithms that minimize false alarms. It not only offers strong cost efficiency by reusing existing optical communication infrastructure, but also ensures uncompromising safety in harsh environments through EMI immunity and explosion-proof design. By integrating ultra-long-distance data acquisition with a calibration-free mechanism, the system minimizes maintenance costs while maximizing overall system availability, delivering an optimal infrastructure solution for industrial monitoring. Subsea power and communication cables are constantly exposed to external threats, such as anchor dragging and localized overheating, making precise condition monitoring essential. Our solution utilizes integrated sensing fibers within the cable to monitor the temperature distribution at joint boxes and mechanical stress along the cable in real time, ensuring the overall integrity of the system. In particular, by integrating DAS and AIS data, the system can identify potentially dangerous vessels in advance, providing an integrated monitoring environment that proactively prevents critical incidents such as cable damage or breakage. By utilizing the idle optical fibers inside existing OPGW and OPPC cables as sensors, this system enables precise, real-time monitoring of transmission line conditions, even under extreme weather conditions. When conductor temperature, wind pressure, or ice and snow loads exceed critical thresholds, the system immediately generates automatic alerts, helping to proactively prevent incidents such as line breakage or transmission tower collapse. Without installing additional sensors, it enables a data-driven and highly advanced maintenance system for modern power grid infrastructure. To detect ground subsidence, internal corrosion, and microleaks that threaten the safety of high-pressure energy pipelines, a fiber optic-based continuous sensing network has been introduced. This system continuously tracks minute strain changes and temperature variations along the entire pipeline in real time, enabling early identification of defects before a rupture occurs and significantly reducing response time. In particular, it can precisely locate leakage points within meter-level accuracy along pipelines extending hundreds of kilometers, enabling immediate safety actions such as automatic valve shutdown and rapid hazard control. In high-risk, explosion-proof environments such as mining conveyor systems, even a tiny spark can lead to a catastrophic accident. For this reason, fiber optic sensor technology, completely free from electrical spark risks, has emerged as an essential alternative. This system is immune to ionizing radiation and demonstrates exceptional response speed, detecting rapid temperature increases to 30 degrees Celsius and 80 degrees Celsius within just 9 and 18 seconds, respectively. By triggering an automatic fire suppression system before flames can spread, it provides an optimal safety solution designed to prevent major industrial accidents before they occur. When daily losses from large-scale pipeline downtime can exceed $10 million, BOTDA precision monitoring becomes a powerful solution for effective risk management. When applied across a 50-kilometer pipeline section, annual downtime can be reduced by up to 80%, while maintenance costs are cut by half, resulting in an estimated $410,000 in annual net savings. Preventing just one leakage incident can immediately recover the entire deployment cost, demonstrating the compelling investment value of this technology. The BOTDA system architecture is built around a compact main unit in a 1U or 2U form factor, featuring 1 terabyte of storage and a low-power design. The ODF, optical distribution frame, serves as a precise interface connecting the control room equipment with the external fiber sensing feed, ensuring stable and reliable signal transmission. The integrated software interface provides real-time graphical analysis and supports industrial communication protocols such as Modbus and IEC 61850, delivering a monitoring environment optimized for industrial applications. Currently, we have implemented FPGA-accelerated machine learning-based precision real-time monitoring across a 120-kilometer sensing range, performing continuous condition mapping without blind spots using standard optical fiber. In the future, we plan to introduce COTDR technology capable of high-speed strain measurement, which will fundamentally resolve the ambiguity between temperature and strain in distributed sensing. Furthermore, by advancing COTDR-based temperature-dedicated sensing technology that complements BOTDA, we aim to establish a highly reliable next-generation infrastructure management system.